Okay, so for part two, we're going to take the Lewis relationship that we found in the previous part, and we're going to find a way to get an energy balance using the Lewis relationship to explain how we find the relative humidity using a wet and dry bulb experiment. So just going to explain that a little further. So using a wet and dry bulb, you can find the relative humidity of a system as long as the atmosphere isn't fully saturated, because the water on the wet bulb will evaporate, and that will decrease the temperature around the bulb, and and we can use that change in temperature to find the relative humidity of the system. Okay, so I just rewrote the Lewis relationship that we found in the last part, and these are just some of the values that we have for moist air. So first thing I need to do is write down the equation for the thermal diffusivity, which is equal to the conductivity divided by the density times the heat capacity. Okay. So we can go back to this definition that we have for the Lewis number, which is that the Lewis number is equal to the mass diffusivity divided by thermal diffusivity. That's not thermal diffusivity, thermal diffusivity. So we're just going to put that in the equation. We're going to multiply by the reciprocal. So that's going to be equal to the mass diffusivity times the density times the heat capacity divided by the conductivity. All right, and so we know, well, we're assuming that the Lewis number in this case would be very close to 1. So this whole thing would be approximately 1. So we can just isolate the two different sets of terms that we have. So we'll have the mass diffusivity divided by the conductivity. There's not conductivity. Divided by the conductivity is equal to 1 over the density times the heat capacity. All right. And so we're going to go back to what we derived earlier. The Nusselt number divided by the Sherwood number is equal to the heat transfer coefficient times the mass diffusivity divided by the conductivity times the mass transfer coefficient. We just showed up here that the mass diffusivity divided by conductivity is equal to 1 over the density times the heat capacity. So we are just going to put that in here and rewrite. So the heat transfer coefficient divided by the density times the heat capacity times the mass transfer coefficient is equal to the Nusselt number divided by the Sherwood number. Okay, and so we can, again, we're assuming that the Lewis number is very close to 1, so we can further divide these out, separate our terms, and then we get this relationship here, that the heat transfer coefficient divided by the mass transfer coefficient is equal to the density times the heat capacity. Okay, and so then from there, we're going to want to take the equations that we have for mass transfer and heat transfer, mass transfer and convective heat transfer. So we have for mass transfer, we're going to want to set them equal to each other because we're assuming the mass and the heat are transferring at the same rate. So for the mass transfer, we have the mass transfer coefficient is equal to the concentration at the surface minus the concentration of the atmosphere. We have it in this orientation where the concentration at the surface is implied to be higher because there would be more water on the wet bulb than on the dry bulb, and that the atmosphere isn't saturated, but the atmosphere around the bulb would be saturated. So we set that equal to the heat transfer, the convective heat transfer equation. So we have the heat transfer coefficient times, and we're gonna do the difference between the temperature at the surface and, the temperature at in the atmosphere minus the temperature at the surface. And you have it in this orientation because the temperature is going to be higher in the environment than it will be at the surface of the wet bulb. If the temperature at the surface is equal to the temperature of the atmosphere, then that is just saying that no water evaporated and that the atmosphere is fully saturated. So we have the temperature of the atmosphere minus the temperature of the surface. Okay, so now we're going to want to look at the units for this. So the units for the mass transfer coefficient would just be meters per second. And for the concentrations here, it'd just be moles per cubic meter. The heat transfer coefficient is in the units of watts per meters, square meters times Kelvin, and the units for temperature would just be in Kelvin. And so we're going to want to have to work our units out. So we're going to have to get some other variables in here that fix our units. So the first thing we're going to want to do is multiply the left side by the heat of vaporization, which is in joules per mole. Let me just do it in a different color. I'm going to multiply by heat of vaporization, which is in joules per mole, and that gets rid of moles for us. And then we're going to have to divide by the mass transfer coefficient over here. So we're going to divide by Kc on both sides. And we're going to get this new equation where the heat of vaporization times the difference in the concentrations is equal to the heat transfer coefficient over the mass transfer coefficient times the temperature of the environment minus the temperature at the surface. And we'll notice here that we just found this relationship earlier, so we can go ahead and put in the density times the heat capacity in this equation. So let me rewrite it again. So that'll be equal to the density times the heat capacity times the difference in temperature. Okay, so now we're going to be using the pressure and the ideal gas constant to find this difference, the difference in relative humidity. So we're going to use the ideal gas law equation. So this will just be equal to the pressure of the water at the surface divided by the ideal gas constant times the temperature at the surface. And it'll be the same for the environment. So pressure of the water at the environment times the ideal gas constant times the temperature of the environment. And density, we can use the density, and that'll just be the total pressure divided by the ideal gas constant times the average temperature. And so for this purpose, we're going to assume that the temperature of the surface is approximately equal to the temperature of the environment, which is approximately equal to the average temperature. That way we can just cancel some of this out. So we'll just say that this is equal to the average temperature, and this is also equal to the average temperature. And then I'll rewrite it so it's a little easier to see. So you have the heat of vaporization times the pressure of water at the surface divided by the ideal gas constant times the average temperature minus the pressure of water in the environment divided by the ideal gas constant times the average temperature is equal to the total pressure divided by the ideal gas constant times the average temperature times the heat capacity times the difference in temperature. And you can see that we will have the denominators of these variables will all cancel out because it's on both sides, and we will simply be left with our balanced equation that the heat of vaporization times the pressure of water at the surface minus the pressure of water in the atmosphere is equal to the total pressure times the heat capacity times the difference in temperature.